everyone. Welcome to Chapter 5 material. We are going to go over Section 5.1 in your book. Hopefully you've already read and studied this chapter or this section. Just a quick review. The number on the periodic table that is below our symbol here is our atomic weight or our atomic mass. So we're going to be using this number quite a bit through this chapter, so be sure that you remember that. The number comes from all of the averages of all the isotopes of a specific element, as stated for you in your last unit. The units for the atomic weight and atomic mass can be AMU. All that means is atomic mass unit. Okay, but what does these numbers mean? What is 24.3? What is that based upon? And that's what we're going to look at here. So the mole. The point of the section 5.1 is about the mole. What does this mean? You may have heard this in previous chemistry classes and so forth, but what does this mean to us? Okay, and in chemistry, we have to deal with an enormous number of atoms in real life situations. So even in a small flask, there are thousands of atoms in that flask. And so we need a way to describe a large number of atoms. And so we do this by using the mole. And it basically means one mole is equal to a number of things. Just like if you say a dozen, we think of a dozen eggs or a dozen sticks, whatever it may be, there's 12 things. And so that's what we think about. In chemistry, one mole is equal to Avogadro's number, which is 6.022 times 10 to the 23rd. This is a number that you want to commit to memory and know this off the top of your head. Okay? When we refer to this number, we're talking about particles, atoms, or molecules. So if you hear particles, atoms, or molecules, or if that's asked for you in a question to find the number of particles, atoms, or molecules, you automatically want to think of Avogadro's number, 6.022 times 10 to the 23rd. Okay, so what does this tell us? All right, well, one mole of a pure substance is equal to whatever the atomic weight of that element is on the periodic table. Okay, so we're showing here this is a key concept to understanding how we're going to relate the mole and grams and atomic mass. Okay, so if you go to your periodic table, so here below we have the symbol for magnesium. It has a 12 atomic number, and here's its mass number. Okay, excuse me, it's atomic mass, not mass number. Excuse me. Okay, the periodic table is based upon one mole. So whatever number is on the periodic table, it's out of one mole. Okay, so I can't express that enough. Okay, so all the numbers you see on the periodic table that are the atomic masses for the elements, they base this all on one mole. Okay, so we have this common relationship between all the elements on the periodic table. Okay, so this is very convenient for us because one mole is equal to 6.022 times 10 to the 23rd. So if we go back here for a second, so we've got underlined here, one mole is equal to 6.022 times 10 to the 23rd. Okay, well, one mole is also equal to the number, the atomic mass found on the periodic table. So for magnesium, it's 24.305. Okay, so we have 24.305 AMU. Okay, that's the unit for 24.305. Okay, so let's give me 1 second here. Okay, and so we also can say that this one mole is equal to Avogadro's number, 6.022 times 10 to the 23rd, and here we'll say atoms. Okay, so not only is this number 24.305 out of one mole, it's also equal to 6.022 times 10 to the 23rd. Okay, and we also can look up here, so if you find titanium on your periodic table, you may have to pause me for just a second. Okay, one mole of titanium atoms is equal to 47.88, okay, because that is the atomic mass of titanium. And on the periodic table, every time you look up a number there, it's based upon 1 mole, no matter what. If you use the periodic table for a calculation for atomic mass, it's based upon 1 mole. Well, we can also say that this AMU is equal to 47.88 grams. Okay, so that's going to be important later because we're going to convert from moles to grams. Okay, and if we have 1 mole, we know that's also equal to Avogadro's number. So all of these are equal, so we're seeing this common relationship between grams, moles, and atoms. Okay, this is really important. Okay, so then we can use the mole to measure and to help us describe quantitative relationships among elements in compounds and substances as they undergo chemical change. So this is kind of the main goal we're going to get to at the end of the chapter, but we want to remember right now at the very beginning of the chapter we're looking at the moles, and we know that 1 mole is equal to Avogadro's number, and this is also equal to whatever atomic mass for an element is on the periodic table. Okay, so we're going to work some calculations here for practice. Okay, so if in a problem we were given that we have 4 moles of sulfur, okay, that's a U there, and it asks us to find the number of atoms. So basically, it may ask us find the number of atoms in 4 moles of sulfur. So that's not; these aren't really complete sentences here, but I think you get the point. All right. So the first thing that you always do. So for dimensional analysis, if you think back to when you were doing you were doing inches to feet and inches to centimeters or whatever it may be, you were doing dimensional analysis. And the reason you learn this first is because this is going to be very similar. Okay, you always write out what you know first. Okay, and this time we have to be sure we write units and not just moles, but we have moles of sulfur. Okay, we'll see why this is important later. Okay, we can go ahead and write out our multiplication sign, and we know if we have moles of sulfur on top, that we have to have moles of sulfur on the bottom here so that these can cancel. Okay, and so the key here is that we're asked for atoms. And we know that if we see the word or we're asked for atoms, particles, or molecules, that we are going to have to use Avogadro's number. Okay? So we look at the conversion factor. So you can actually memorize Avogadro's number 6.02. You don't have to use the 22 if you don't want to. Okay? So here we've got atoms. So this is our conversion factor. And we know that we can flip this around, and it's the same thing. We can have 1 mole over 6.02. Okay, so either conversion factor works. So we have to know how we're going to plug this into here. Okay, and since we have to have moles on the bottom, we have to use moles here. So we're going to plug this conversion factor into here. Okay, because we have to have, we're going to plug this one into here. Okay, moles is in the denominator here. Okay, and we have moles in the denominator here. Anytime you use Avogadro's number, it's always based on 1 mole. Okay, so you can't have a 2 there or 3 because that's not what Avogadro's number represents. Okay, and so let me go ahead and erase this. Okay. So now we can plug this in. So in 1 mole we have 6.02 times 10 to the 23rd atoms. Okay, you also want to use your calculators and be sure you get the same answer. A lot of times when we start using these numbers where we have times 10 to the power of a number, students don't know how to plug it in their calculator correctly. So be sure that you plug it in. What you're going to probably have to do is put everything in parentheses. So be sure your answers match up. Okay, so our moles cancel. Okay, we're asked for atoms of sulfur. Okay, so if we do the math here, we should get 2.41 times 10 to the 24th power of sulfur atoms. So we get a really big number here, times 10 to the 24th. So that'd be like moving the decimal place over 24 times. Okay, so that's how many atoms we have in just 4 moles of sulfur. Okay, so now I want you to practice. You can pause the video if you'd like and try to work this one yourself. Notice that this time we are starting with molecules. So we're given the number of molecules of water that we have, and we're asked to find moles. Okay, so the first thing that we always do is write out what we know. Go ahead and draw our next fraction here. Okay. So we have molecules of water. It's not just molecules, we have molecules of water. You'll see why this is important later because we're going to be converting from one compound to another here later in the chapter. Okay, and so this time we still use our ratio. We have 1 mole to or the reverse of this. Okay, so if we see the word molecules, particles, or atoms, we automatically know we're going to have to use Avogadro's number. Okay, but this time we have molecules up top here, so we have to have the number of molecules in the denominator. Okay, and so this is how we're going to plug in. We're going to have 6.022 times 10 to the 23rd molecules. And out of how many moles? Exactly. Good job. 1 mole. Because Avogadro's number is based upon 1 mole, just like the periodic table is based upon 1 mole. Okay. And so if we do the math, take me a second here. I'm going to plug it in. So times 10 to the 22nd. Okay, I'm putting everything in parentheses. Okay, so we should get about 0.08. So we've got 3 significant digits, so we want to have 3 here. Okay, and so I forgot my moles of water there. So moles of water. Okay, so I'm going to check that one more time. 4.85 times 10 to the 22nd. About 6.022 times 10 to the 23rd. Yep, gives us 0.0805 moles of H2O. Okay, go to your textbook for more practice. There's also a handout that has an outline, notes, and practice problems to work on your handouts and extra practice tab in Blackboard. So this is a great place to go for more practices as well. Thank you, and I will see you in the next video.